Welcome along, ladies and gentlemen, to your weekly SETI seminar series. Today we're lucky enough to be joined by Sergei Dubovsky. And he's at Stanford University. He's going to talk to us today about black holes and string multiverse theory. Sergei started his career in theoretical physics at the Moscow Institute for Nuclear Research. He then moved to CERN to work more on theoretical physics and particle physics. And then he moved across to Harvard. And after that, he progressed to his postdoc at Stanford, where he's been working on looking at black holes using string theory. And he's going to talk to us about that subject today. So if you'll join me in welcoming Sergei.
Yeah, I would like to thank the organizers for inviting me here. It definitely promises to be a very interesting experience for me. I'll try to do my best to make it entertaining for you as well. And I ask you, please do ask questions, because that will help me to see where I'm going too fast or too slow, and it's always good to have feedback. My talk will be organized as follows. So most of the talk will be more on the theoretical side, so I will explain what this string multiverse idea is, and what are theoretical and observational origins of this idea. And I should say that it's probably one of the most controversial subjects right now in theoretical physics, and so different people have different strong opinions on this. Some think it's not science, some say hate it, some love it. But well, our attitude was, just as for any other idea in physics, we want to see how to test it, whether it's testable or not. So the second part of my talk will be about quite interesting ways to test these ideas, which came out recently by black holes observations. But to start with, let me start with a bit of philosophy. And all scientists probably know about this guy who proposed what serves as a routine method in any scientific research now, that whenever you want to explain some phenomena, you're trying to do it with the least possible of ingredients possible. And definitely this is a very practical and useful tool, but that doesn't necessarily mean that that's how nature works. And actually, for hundreds of years, there was debate in philosophy. So there were people who, well, also scientists, who were promoting the opposite point of view, basically saying that all possibilities should be realized in nature, and there is no reason to expect nature to follow some minimalistic or simplistic path. And so this was, for a long time, this was a debate in philosophy, but from time to time, also in physics, we see clash of these two ideas. And so actually, one of the points of my talk will be that it's likely that right now in physics we're at the moment when like these two different philosophical ideas are going to be tested against each other empirically. But that's not the first time that it happens. So actually, one somewhat very similar situation happened like 500 years ago, when so people realized that there are many stellar systems around us. And for thousands of years, people thought that one of the questions for science or for physics or metaphysics, whatever was there at the time, was to explain the solar system, to explain the size of the planetary orbits, ratio of Earth's orbit to Mercury orbit. But after Copernicus, it became clear that this is not an interesting question in physics, because there are many stellar systems around, and so the one where we happen to live, so to some extent clearly selected by some environmental reasons, just that there is a planet which is located at the convenient distance from the star, so there are good conditions for life, and there is nothing unscientific in that, of course. It's just tells us that these questions, which people thought are relevant for physics for many years, are not relevant. And there are other questions like dynamics of the different stellar system, etc., which are interesting physics questions. And just like now, at that time, well, different people have different strong opinions on the subject, and some people were really fired, literally fired, for pursuing these ideas. So, yeah, let me explain now why situation in physics now, to some extent, similar to this conflict. And actually, at the moment, we don't really know for sure which is the right attitude in the present case. But the two major mysteries in temporary and in nowadays cosmology and fundamental physics is the origin of dark matter and dark energy. So what is shown here, the energy budget of the universe, the percentage of different stuff which universe is composed of, and so you see that the stuff we are made of, like atoms, gas, is just about 4% of the total mass in the universe. On the other hand, so there are 23%, what is called cold dark matter, and 73%, which is called dark energy. So let me briefly explain you what are the observational evidences for these two components and how do they behave. So dark matter seems to be rather conventional thing. So the classic observational evidence for dark matter is that people look at the galaxies, they look at the velocity of the stars rotating around the center of the galaxy, and by measuring this velocity, then you can try to reconstruct the mass profile in the galaxy. On the other hand, you can just look at the stuff which is in there, at the stars, gas, and what happens that so this red curve would be the theoretical prediction that what you would expect if you add up all the mass which is in the galaxy of stars and interstellar gas. On the other hand, for many galaxies, the actual velocity profiles, they look something like that. So one interpretation for this observation would be that there is actually some missing mass, some mass which we are not seeing, which is roughly spherical halo around this galaxy, and that's what contributes to gravitational field. So it gravitates, but it's not some usual stuff. It's most likely some particles which very weakly interacting, and we see them only gravitationally. So and actually, so there are lots of observational evidence for this interpretation, favoring this interpretation. For instance, what is shown on the right is quite, I think, remarkable picture. So what's shown here is so-called bullet cluster. This is there are two galaxies which collided one with each other and passed through each other. So what you see here, so this red stuff in the center, that's gas. So it's most of baryonic mass in each of the galaxies actually composed not of the stars but of the interstellar gas, and even two clouds of gas pass through each other. They interact inelastically, so you see they didn't quite pass through each other. So there is a cloud of gas which stayed in the center. Now, so here and here in these blue regions, first of all, you see a bunch of stars. So stars, they don't interact much, so they just go through each other. They act as like non-interacting gas of particles. So they passed much further away than these two clouds of gas. But most interestingly, so what these blue clouds supposed to show you that there are other methods how you can see how mass is distributed in this object. So basically you can use gravitational lensing, the fact that mass curves the light when it passes by. So by using gravitational lensing, you can deduce where actually most of the mass sits in these galaxies. And it turns out that it sits in these blue regions. So you find that what happened, that there was the largest actually fraction of the mass, it followed stars. It didn't interact, didn't get stopped in the center. So it behaves as essentially non-interacting gas of particles. But these are not stars, because stars are by far not enough to account for the whole mass which you see here. So this this picture clearly supports this idea that there are some particles in nature which not interacting by usual interactions, but they gravitate and constitute. So when you plug in numbers and do careful analysis, so there are different ways to get this number. You get that about 23% of the mass is composed of these particles. So by itself, it's not that mysterious. Okay, there is some different new sort of particles, and it's interesting to detect them directly in the laboratory. But probably more mysterious component is what is called dark energy. So what's shown here, so on the left-hand side, what's shown here, so it's basically this is measurements of expansion rate of the universe. So you pick up particular kind of stars which roughly look as standard candles and look at the brightness as a function of distance to us. And so this red circles are data points, and the different lines, they correspond to different matter energy content of the universe. And what you see is that the best fit to this data point is the upper curve, which corresponds to situation when 25% of universe is composed of matter, but 75% composed of very interesting substance which have, unlike all usual matter, it have negative pressure. So in other words, when you have expansion of usual stuff, you expect that the expansion rate will decelerate if you go further and further, just because gravity is an attractive force. What we see actually is that the expansion rate is accelerating. So when you look at the further away stars, they go faster. Well, they go faster because of the Hubble law, but also if you look at the derivatives of Hubble law, you find that there is acceleration. So it looks like there is some component in the universe which have negative pressure. Well, this plot by itself may be not that impressive. At the end, there are quite significant error bars here. But already at the time when these observations came out, there were lots of evidences for independent evidences pointing in the same direction. And actually, now we don't even need this supernova data to conclude that the expansion of the universe is accelerating. So what's shown on the right-hand side is, I think, much more compelling plot. So here, so what combined here is data from measuring relic photons from CMB photons. This is WMAP. This is satellite which was measuring relic radiation with very high precision. And also, so this SDSS, this is basically counting galaxies in the universe. So this is huge galaxy surveys which collected a database of huge number of galaxies. And by looking at the spatial distribution of these galaxies, you can also gain some information about expansion of the universe. And you see here that, so this is the allowed region. So the axis here, again, on the vertical axis is the fraction of this dark energy component, and this is the total matter component. And you see that the allowed region indicates that there is about 70% of this dark energy. So what this could be, and there is a very simple and natural candidate for dark energy, namely, if one says that vacuum itself, when there is no particles around, that if vacuum has non-zero energy, then basically even from special theory of relativity, and of course it's gravity, so it's from general theory of relativity, follows that the equation of state for vacuum necessarily implies that there should be pressure which is equal to density and have opposite sign. So really the simplest explanation for all these observations would be to say that vacuum has non-zero energy. And the number which one needs is, so there is some number which is actually quite tiny, 10 to minus 29 gram per cubic centimeter. So one can think, well, okay, one of the purpose of physics is to calculate this number from the first principle, to predict this number. Well, at the moment we can't really do this because you basically need to know all theory of physics, because whatever is in your theory would contribute to this number. But what we can do, we can calculate different contributions from the parts which we know to this number. And what we find is there are contributions which are huge compared to what actually observed. They are larger than this number by 50, 100 orders of magnitude. So basically this is very dramatic breakdown of simple dimensional estimates in physics. So you do some simple dimensional estimates, you're not calculating the whole thing, you're just calculating different contributions, but you find that there are contributions larger by 100 order of magnitude, which what you actually find. So that sounds definitely very puzzling. Furthermore, so if you look at the history of the universe, if you look at the ratio of matter to vacuum energy density, so then as universe expands, these two components, the two densities, they change differently, because if the universe expands, matter density, so matter density is just density of usual stuff, particles. So if you expand the box of particles, you dilute stuff in there. So the matter density dilutes as the universe expands. On the other hand, vacuum energy, it's a property of the vacuum, so it doesn't change as time goes on. So this ratio matter to vacuum energy density, it quite rapidly changes over the history of the universe. And so what's shown here, so this star corresponds to current to us, something like 13 gigayears. And you see this, so this ratio, it's about so 1/3, but it's very close to 1. So we happen to live in a very special moment of time when this ratio of these two quantities, which quite recently on cosmological timescales was by far bigger and will be by far smaller very soon, it happened to be of order 1. So that also sounds interesting. And well, there were different dynamical models, so people tried really hard to come up with dynamical explanation for these observations, but I think it's fair to say that at the moment there is no successful theory which would predict these two numbers from the first principles. Well, on the other hand, there was an argument which was put forward by Steve Weinberg in late 80s, actually before this vacuum energy was observed, before acceleration of the universe was observed, and the argument was the following. So roughly this is the period when galaxies were formed. Now, if vacuum energy were bigger by a factor about 100, then it would dominate expansion of the universe before galaxy formed. What that means, so the way galaxy formed, so you have in early universe was very homogeneous with very, very small inhomogeneities, fluctuations in density, at the level 10 to minus 5. Now, because gravity is attractive force, the small seed inhomogeneities, they grow as time goes on and give rise to all the structures which we see in the universe, in stars, galaxies, clusters of galaxies, etc. Well, on the other hand, if in such a situation, if this accelerated expansion takes over too early, when these inhomogeneities are still very small, then they don't have time to grow. They got all diluted by accelerated expansion of the universe. So if vacuum energy were bigger by factor of order 100, then it would be a very boring universe. There would be no galaxies, no structures. So it seems, at least life, the way we know it, wouldn't exist there. So maybe that explains just so maybe this indicates that just like the question why the Earth-Sun distance is the way it is, it's not really fundamental physics question. Maybe this indicates that the same true also for vacuum energy. And that would also naturally explain why you expect matter to vacuum energy to be of order 1, because, well, there is a pressure to have large vacuum energies, there are large contributions there, but they all need to cancel for galaxies to form. And actually it's quite interesting. So this paper was published before actual observation was done, and really the way this paper was written was to falsify the application of anthropic principle to a cosmological constant problem, to vacuum energy problem. So what Weinberg argued is, if we were not to find acceleration of the universe, if we find that vacuum energy is much smaller than the bounds, the observational bounds at that time, that would indicate that so we really have to understand what is the vacuum energy. So that means that anthropic arguments are not applicable to that. Well, instead what was found that universe accelerates, expansion is accelerating, and the vacuum energy is close to matter energy. So these arguments actually work quite well. So again, to bring the connection with what I was saying before, so if you look about some minimal theory, roughly, so here I'm showing roughly the potential, the energy of the theory, so we're supposed to live in one of these vacua. So if you see that the vacuum energy is very, very close to zero, then in such minimal setup, this is a puzzle. This is something which requires dynamical explanation. You need to find a reason why vacuum energy is so small. On the other hand, if you live in a universe with very complicated potential, with huge number of possible vacua, where we could live with different laws of nature in different vacua, then this anthropic argument by Weinberg is applicable. So it's not a puzzle why we happen to live in the vacuum where vacuum energy is so small. It's just because galaxy can exist only in such a vacuum. So for this argument really to work in the present context, you need something of order 10 to 100 vacua, because the observed value of the vacuum energy is by 100 orders of magnitude below the natural value which you expect. So this was observational situation, and on the other hand, on the theoretical side, in string theory, it was realized that, well, string theory is the leading candidate for theory incorporating quantum mechanics and gravity right now. I think actually it's the only working example of such a theory. So what was found that actually this theory really possesses what was called landscape, so or something like 10 to 500 of vacua, and actually this number is continuously changing. So a couple of weeks ago I was at a seminar where it was more like 10 to a million. And there is a big difference between 10 to 500 and 10 to a million. But for my purposes here, it doesn't really matter. So it was really found that this theory has this huge landscape. And as I said, some people really hate this, some love it. But so the question we're trying to ask, how you test it, if that's true, and it definitely goes in the direction suggested by this observation of the accelerated expansion of the universe. So actually you don't need to know that much about string theory to see how this 10 to 500 vacua come about. So what you need to know, one fact about string theory which you need to know, that this theory predicts that there are extra spatial dimensions. So this theory it's inconsistent, it's just 3 spatial dimensions one time. So you need, well, depends on how you call it, but roughly you need in total 10 or 11 dimensions. So one time and extra 9 or 10 spatial dimensions. So of course that doesn't agree with what we observe. But the way to solve this problem is to say, okay, out of these 10 dimensions or 11 dimensions, 6 spatial dimensions actually compactified. They have a shape of some compact manifold, compact surface, and they are so small that the resolution of experiments which we are performing is not enough to resolve their presence. So the second ingredient which you need to get many vacua, you need that this compact space, which we didn't discover yet, so it should have complicated topology. Well, and there are different reasons how this comes about. By topology, I really mean that, well, there should be lots of, in two-dimensional case, would be lots of handles, lots of non-contractible cycles in this compact manifold. So the way it comes about, so one way, very bottom-up way is that when you just try to get out of string theory something which resembles real world, so the current theory of particle physics, it's quite messy. So there are lots of particles. So it's quite a mess. So to get such a mess from this 10-dimensional theory, well, you need to choose the compactification, which is quite complicated. But also, just on purely combinatorial grounds. If you have 6-dimensional compact space, which you are not choosing something, the simplest one like sphere, but if you have a little bit of imagination, that just on combinatorial grounds you find lots of low-dimensional subspaces, surfaces, handles inside the 6-dimensional space. So for instance, if you take 6-dimensional torus, that you will find for the few tens of different what I call cycles here, namely you can look for instance for different 2-dimensional torus and 6-dimensional torus. Just on combinatorial grounds you will find many. And so the numbers I will need here actually something for the hundreds. That's what typically comes out in string construction. So I need this compact extra-dimensional space to have for the hundreds of internal non-contractible cycles. Now the third ingredient which one needs is gauge field. So one example of gauge field is photon, but in string theory on top of that you have high dimensional generalization of photons. So just like if you have a point-like charge, it couples to a vector. Naturally, the world line of point-like charge coupled to a vector. In string theory is a theory of extended objects. So it naturally has fields like photon, but with more indexes, I mu, lambda, rho, just because it has extra-dimensional extended objects, not just point-like particles. So that's the third ingredient which you need, and actually these 3 ingredients are enough to give the landscape of 10 to 100 vacuum. And the way to see it is the following. So if you have these internal cycles in the manifold, what you can do, you can start turning on basically fluxes of magnetic field through these cycles. And so magnetic field, so the flux of magnetic field, it's in quantum theory, it's always quantized, so that you can turn on several units of flux, and there is a maximum value which you can turn on, because when magnetic field becomes too large, the whole construction becomes unstable. You start producing particles. So typically, you have like up to 10 units of flux is very reasonable to be allowed to turn on. But so if you have 100 of cycles in your manifold, and for each cycle you can turn on up to 10 values of units of fluxes, that gives rise to 100 different configurations, and each configuration has different energy. So that's exactly what you need to get 10 to 100 of vacuum with different energy to solve cosmological constant problem. So these are really ingredients which come into this string landscape, and that's at least the known string vacuum. That's actually how they're constructed. So yes.
Each multiverse will come with this in this manifold that you've got represented, and then there'll be multiple manifolds for each.
Well, so now different vacuum, they would differ by the number of these fluxes which you turn on. But so as you start turning on fluxes, your manifold get a bit modified. Also, there are other ingredients which you can put on this picture, like so in string theory, as I said, there are extended objects, membranes, which you can wrap around different cycles. So like each particular vacuum will be described by choice of compactification manifold, choice of number of fluxes, and choice of these extra ingredients which you put in, and so what by multiverse we call the whole thing, and in each particular vacuum, when you go to long distances, long compared to the size of this manifold, you find some physics described by some theory of particles, but they will be different depending on what are the ingredients which you put in here. So the one observation, so it's very hard. The problem is, so you have all this vacuum, but the difference with what happened in my example with other stellar system, so there we can see directly on the sky and see these other stellar systems. So in case of this different vacuum, it turns out to be extremely hard to see them directly. So people thinking about like looking for traces of bubble collisions, when the bubble of different vacuum collides with our vacuums, then you can try to see the remnant of that. But you need to be really very lucky for something like that to be observable. So it's very hard to see it. So what one can try instead, one can try to see whether the same dynamical ingredients, namely extra dimensions, gauge fields and complicated topology, where they give to some other observational consequence. And that what was called string Axiverse. Namely, it was noted that actually the same ingredients give to expectation of tens or maybe hundreds of light particles, they're called axions, in our vacuum. So let me explain you how this comes about. So first of all, how what we call particles in general, in four-dimensional world, how it comes out from this picture. So particle is some excitation, some field configuration which has some profile in this extra-dimensional space. So it can be really some excitation of geometry which propagates, like some sound wave which propagates on this manifold. It can be non-geometric, some perturbation in electromagnetic field which propagates on this geometry. So from four-dimensional point of view, that looks what we call particle, because we cannot resolve its extra-dimensional structure. So we just see a point. We don't see that it corresponds to actual fluctuation on this compactification manifold. Now, let me remind you about something very well known from electromagnetism. So let's just consider solenoid. If you have a solenoid, then there is a magnetic field inside the solenoid, but outside there is no magnetic, no electric field. So locally, the electromagnetic field conversion is pure, it's gauge trivial. But nevertheless, you can, without going inside this solenoid, you can detect the presence of this magnetic flux inside. Namely, this is the famous Aronoff-Bohm effect. So if you look at the scattering of charged particles of the solenoid, then when it goes around the solenoid, it picks a phase in the wave function, which is observable in quantum mechanics. So there is a scattering. Even if outside there is no actual magnetic or electric field, you still see physical effect when you scatter from the solenoid. So this is just the same picture from the top. Because there is a magnetic field is only inside the solenoid, the energy of solenoid is concentrated inside the solenoid. There is no energy density outside. So imagine that what you did, you cut out a hole. So you took an electromagnetic field configuration that doesn't have actual solenoid, but your space has a hole such that outside field configuration is the same as it was for solenoid, but there is nothing inside, literally nothing. That means that there is no energy density associated to this thing. But still, this is a physical field configuration. As before, you can do scattering of electrons and you still will see a physical effect. So what that means, so if you organize this kind of configuration in your compact extra-dimensional space, and the role of hole is really played there. You don't need really have boundaries there. It's enough to have these non-trivial cycles, non-contractible handles in your manifold. What you will find this will be non-trivial field configuration because it has physical consequences, but it doesn't carry energy. So it corresponds to massless particle from four-dimensional point of view. So that tells you that the same ingredients which give rise to this plenitude of vacua, they also give rise to not to 10^100, but roughly tens, hundreds of particles. So in this approximation, they are massless. Now, there are tiny contributions which make this particle massive. So roughly, so in this situation, if you consider there is a loop of virtual electrons. So you may imagine electron-positron pair created here, and they go around, not real electrons, but virtual electrons, which go around this hole and annihilate on the other side. So this kind of configuration will contribute and give rise to a tiny mass to this hole, which otherwise doesn't have any mass at all. So this gives rise to expectation to many particles, which roughly they give us information in our vacuum about this topological complexity of the manifold, which was also responsible for multiverse. And actually, so this is probably going to be the most complicated formula which I have. So there is a hint from nature that such particles exist. So what is written here, you don't need really to care what is written here. It's some term which you can add to to series of strong interactions. And it has many interesting features, but the most interesting property of this term is probably that, so there is a coefficient, some coupling strengths, which you can put on front, which characterize how much of this term you added to your theory. And there is a very strong limit on this coupling. Namely, if this term was there, the neutrons would have non-zero electron dipole moments. And people were looking for electron dipole moment for neutron and didn't find any. And if this term there, that actually neutron, so actually what happens that the contribution to neutron electron dipole moment, it's sum of two things. It's sum of this coefficient here, and on the other hand, so in series of strong interactions you have quarks, and quark mass matrix, actually it's a complex matrix, and the fact it's complex, it's related to the fact that T invariance and the time inversion is not there. It's broken in nature, and we know. So this matrix is indeed complex, and the observable quantity is not this parameter itself, but the sum of this parameter, and overall phase of the determinant of the quark mass matrix. So this sounds very similar to cosmological constant problem as I described to you before. So again, there are two quantities which come completely from different sectors of the theory, which a priori could be of order 1, actually. So this theta is a periodic parameter, so theta equal to 0 is equivalent to theta equal to pi, so it can take any value between 0 and 2 pi. But on the other hand, what we find that the sum of these two quantities somehow miraculously turns out to be 10 to minus 10. So that's another example of very similar, what's called in physics, fine-tuning problem. But unlike for cosmological constant problem, it seems there is no anthropic reason. There is no reason why having this thing of order 1 would make any harm to life. And actually it would help because to create baryon asymmetry, we're all made of baryons and there are no antibaryons around, and to create this asymmetry, one of the ingredients which you need violation of time reversal symmetry, and so having theta large is actually, it would help, but so clearly there is no problem of having it for the 1 and not 10 to minus 10. So this is clear call for some new dynamics. So it's clearly, this fine-tuning problem clearly cries for being explained dynamically. And there is a very nice dynamical solution, which was called Axion. So basically what you do, you say, so there was this parameter theta, but you say, okay, it's not a parameter. Let's call it field, like we have fields in our theory, electromagnetic field, gravitational field. So this will be a new field, so let's make it dynamical. So when you make it dynamical, what you find, so now you need to minimize the energy. To find your vacuum, you need to find the value where the energy is minimum with respect to this parameter theta. And what you find, that the energy is minimum exactly when this quantity theta bar, which contributes to electric dipole moment, is 0. So that's a very nice dynamical solution to that fine-tuning problem. Unfortunately, we don't have anything like that for cosmological constant problem. But also it's predictive, because so you pay a price when you promote parameter to a field. It means that now you can excite this field from the vacuum. In other words, you predicted the existence of a new particle, and this particle, so it's in this present context called QCD axion. And it turns out, so this particle, so it has, so these light particles I was talking before, they have lots of properties very similar to this QCD axion. They have very similar interactions and lots of properties which you expect from the QCD axion. Well, on the other hand, and actually that's how this mechanism, this topological mechanism with Aronoff-Bohm effect, which I explained before, that's how axions come out, QCD axion come out in string theory. But that really suggests you that if you expect, so because as I said, there is no anthropic reason for QCD axion. That means it should be, if it is there, and there's strong indication to think it's there, although it wasn't found yet. So if it is there, then it shouldn't be exceptional. It shouldn't be fine-tuned in this compactification manifold. So to start with, you expected to have hundreds of those light particles. So it would be really strange if only one of them survived. that means that taking seriously QCD axion and properties of axion in string theory, one expects, so what we call Axiverse, to see many light axions. And I should say, of course, so people were tried to look for QCD axion. So there are two parameters which characterize it: the mass and the strength of its coupling. And so when it's coupling, so this is the scale which characterizes the strength of the coupling. When the scale is small, then there are lots of laboratory and astronomical constraints on it. But the most interesting region in string theory is when scale is large. It's somewhere here. So this region is most interesting from theoretical point of view, but also, as I will explain right now, so there is some interesting connection to anthropic reasoning, which comes out in this range. So okay, let me skip this. So let me tell you now about relation. So we're coming back to dark matter. So what axions has to do with dark matter, and what was this anthropic thing which I have shown there? So if you think about history of axion as the universe was expanding, as the universe was evolving, then so there is no reason why originally it would sit in its minimum. It's like originally universe, very early on, universe was hot, so all particles were strongly interacting. So this was some field which you expect to be perturbed, not to sit in the minimum. Now the very interesting property is that, so basically you have this potential for this field, it wants to roll down, but expansion of the universe effectively acts as a friction for this field in this potential. So this system, it's not this is not a conservative mechanical system. You have a friction due to expansion of the universe. So at early times, if in some region of the universe axion was displaced from the minimum, it would just sit on the slope of the potential. It would be frozen because friction is too big. The universe expands too fast. Now, what happens later on, then as the universe expands, the expansion rate slows down, then the axions start oscillating, and you produce. So what you have in your, so it doesn't really end up here, just amplitude, because of friction, amplitude of oscillation drops down, but there will be always some oscillations. And actually these oscillations, so alternative way to describe this oscillation is to say that you produced lots of axion particles. It's really, so this was a field description, but in particle description, that means that you produce lots of particles from the vacuum which just sit there, and they act as a cold dark matter. So this oscillating scalar field, it plays the role of cold dark matter. But the interesting point about this particular cold dark matter, that the amount of dark matter is determined by local initial conditions. Namely, how much dark matter you will end up having determined how high you are sitting on this potential. If you were sitting high, then your initial energy density was large, so you have lots of dark matter. If you happen to sit very close to the minima, you will have very few of dark matter. Now it happens that in the universe we live, we find that dark matter to density, to baryon density, that's a factor of around 5. That's another interesting coincidence. Why these two numbers are approximately of the same order? And again, one way to say to answer this question would be to say, okay, if this ratio was smaller than 2.5, and it turns out that galaxies do not form again. So basically, because when you have less matter, then dark energy would take over the expansion earlier, and galaxies wouldn't have enough time to form. On the other hand, if this ratio were about 100 times bigger, then what happens? So in the galaxy, so you have this spherical halo made of dark matter, and you have baryonic disk where star forms. But the way star forms, that you have stars forms that you have gravitational instability. So you form this disk, but then it collapses in individual clumps of gas, which give rise to stars. But if this ratio were bigger than about 100, then what happens is that the halo is so massive that it stabilizes the disk. So this disk doesn't fragment and you don't form stars. So again, you find the region where you expect to be, just because otherwise there would be no galaxies, no stars. And we found the value of 5, which is actually, so you can, so in the universe with Axion, you can try to predict what is the value, what is the value which you expect. So the picture of this universe with axions is that in different regions of the universe you have different values of this ratio, because in different regions of the universe initial value for the axion field would be different. And what was interesting about this anthropic region for axion, which I was showing there, that there for typical initial value, you find actually too much of dark matter. So to have this value 5, you need to be very close to the minimum. But so what is explained here is a good explanation for that, because it couldn't be much bigger than 100, and with just one axion, actually, what you find that the probability to find the observed value around 30%. So it's perfectly consistent with what we see. Now, I told to you that this string theory, and in string theory you expect actually to have more of these axions. Not all of them should be anthropic. So for some of them, for light axions, what happens that even they have a cosine potential. So even if you sit at the very top, you still produce very little of dark matter. So what we are interested about here, you care about axions in the anthropic region, which would naturally produce too much of dark matter. So as you increase the number of axions, actually you have a pressure that there should be more and more. This ratio you expect it to be larger and larger. Intuitively, so for one axion, basically you have the whole allowed range of values, and you look for a probability to be close to 0. Okay, it's ratio of the field, range of field values to be close to 0 to the whole allowed field range. But now for two axions, you now want to be inside of a small circle about the origin. For 3 axion, a small sphere. So you pay larger and larger price because there is a volume factor, just because the size, the ratio of the small volume to the whole volume is becomes smaller and smaller. It's a fixed radius ratio. It becomes smaller and smaller as you increase the number of dimensions. So for instance, for 2 axions, this probability drops to 16%. And if we were to find something like 10 axions, the probability to find the observed value would be around 10 to minus 6. So in other words, when you increase the number of axions, there is a pressure to have this dark matter to baryon ratio to be as close to the what's called anthropic boundary, to the boundary where life formation is not possible, as possible. So the conclusion, so we don't know yet, but there is an extra interesting possibility. So finding more than 4 axions in this anthropic regime would be a problem. So 4 axions correspond to probability around 1% for the actual dark matter to baryon ratio which we observe. So, but it's still a possibility. We don't know. We didn't measure yet. So I will tell you about measurements later on. How can we look for these axions? So imagine that we found more than 4 axions. So we should reconsider something in the previous line of reasoning. So what are the main ingredients to reconsider? So actually, in constructing these curves, which I was showing you before, so the main ingredients which went into these curves was the following. So basically, in this whole, so first of all, you need to specify this anthropically round region, this dark matter to baryon ratio from 2.5 to 100. And actually, this wasn't studied much. So these are really estimates at the moment. But furthermore, if you believe these numbers, then the way you argue, you say, okay, the number of observers which you expect to the universe should be proportional to the number of stars, and those should be proportional to the number of baryons. And that holds in this whole anthropically round region, which, of course, so for instance, this part is clearly very crude approximation. So the properties of the universe change a lot when you vary this ratio, dark matter to baryon ratio, by a factor of 100. So clearly there is lots of astrophysics involved here, and that's the first thing one should reconsider. But another part, which, which I don't understand much, and probably people here may have a better opinion than me, but which sounds fascinating for me, is the following. So also this relation is not obviously true. It's not obviously true that the number of observers is proportional to number of stars, because it seems that, so that would be definitely true if life evolves separately on different stellar systems. But on the other hand, the distance from our stellar system to the next stellar system in our universe, it's not that big. It's the parsec size. So you can imagine that for life evolution, it's actually easier to form some, say, primitive form of life on one stellar system and then to transfer that to another stellar system. In such a situation, the number of observers would not scale linearly with the number of stars, but would scale as some higher power, and which would modify these arguments. Which would change this number 4. So what this number 4 assumes? It assumes that basically, among other things, apart from this astrophysics part, it also assumes that life were evolving individually on different stellar systems. And that sounds, for me at least, something which can be checked and tested. And as far as I know, it's not an answered question so far, whether evolution was, well, basically, if that's part of explanation, if we find many axions and that is part of explanation how it can be, then you expect to see remnant traces of life formation in the vicinity of the solar system. Okay, so let me now spend the rest of my time to explain to you how to look for these axions. And actually, so here, what is shown here is a mass. So horizontal axis is the mass of the axions, and there are different ways how you can look for that. But this gray region, this is the especially interesting region. These are axions with this mass. They're anthropic. So finding too many of them in this region would be a problem. But also, actually, QCD axion you expect to be somewhere here. So I will focus only on this region, and there is a very interesting process which allows to look for axions in this region, which is called black hole superradiance. And so the observation is the following: for axions in this mass region, the Compton wavelengths of this particle. So the waves, you can think about them as particles, but you can think about them as waves, and Compton wavelengths of these particles matches the size of astrophysical black holes. So in nowadays astronomy, observations of black holes is really routine. So there are stellar mass black holes, and there are around 40 non-stellar mass black holes in binary systems in our galaxy and in close by galaxies. And also there are black holes, super heavy black holes, and they're believed to be in the centers of most galaxies with masses from maybe 10 to 6 solar masses up to 10 to 10 solar masses. And people do observe them, and moreover, recently people started, so you can measure the masses of black holes by looking at the stuff which rotates around, but also you can measure the spin of black holes by studying the details of accretion disk, how the matter accretes on the black hole. And that's what people started doing recently. They started getting spin measurements. And so as I will explain now, actually each black hole serves as a kind of detector for particles with a mass range such that their Compton wavelengths roughly matches the size of the black hole. So to see how this comes about, so let me remind you about one rather famous process in general relativity. Namely, this is a picture from Misner, Turner, Wheeler book on gravity. So if you have a rotating black hole, then you can extract energy from this black hole. Namely, what is supposed to be happening here is that you have advanced civilization living around black hole, and it sends cars with trash to the black hole and aims them very accurately. And so around rotating black holes there is a region which is called ergo region, where all matter should be rotating. It's not possible not to rotate when you are there. So when you enter in this ergo region, you can throw away trash into the black hole, and if you're doing it carefully enough, then what happens that as a result you gain energy, you extract rotational energy from the black hole. So black hole spins down, and you gain energy. So the car comes out faster than it came in. That's all very amusing, but doesn't sound very practical. Another unpractical application for the same process was suggested also in the 70s by Press and Tikolsky. Namely, the same process, so this was for a particle, for this car falling in there. But the same process exists also for waves. So if you just, for instance, take a photon and try to scatter of the black hole, then there will be certain parameters, certain angular moments of the incoming photons and frequencies, such that as a result of scattering, the outgoing wave will be stronger than incoming. So black hole doesn't absorb but enhance the incoming wave. So you're creating new photons. You started with one photon, but you created two photons as a result of scattering. So this is also possible. This is basically the same process. So what Press-Tikolsky suggested that gives rise to what was called black hole bomb. So if you take a rotating black hole and surround it by a spherical mirror, so then this whole system will be unstable now, because if you put there a single photon with the right quantum numbers, then it can go to the black hole, and as a result of scattering of black hole, you create two photons. They're trying to escape, but now because there is a mirror around the black hole, so they bounce back. So and the process repeats. So you have exponentially growing number of photons. So basically inside this spherical mirror, you create, there is exponential stability, you create a laser. So you create lots of photons in the same, with the same quantum numbers. And at some point there will be so many photons that mirror will blow up. So that was the Press-Tikolsky proposal. Again, this doesn't sound very practical, but the amazing thing, which was also actually noticed in late 70s, is that nature itself may provide such a mirror. Namely, if instead of a photon you took a massive particle, if particle has a mass such that its Compton wavelengths of order the size of black hole, then effectively this mass acts as a mirror. And the reason is that, so we all know that for massive particles it's possible to form closed orbits around black holes. So you can think of taking a wave packet of massive particles, put them on a closed orbit, closed Keplerian orbit around black hole. It will be rotating, but because it's a wave, there will be always a tail of the wave which goes close to the black hole, to ergosphere. And for certain orbits, it would get amplified. So if you have a massive particle with Compton wavelengths of order the size of black hole, then what happens that black hole starts spinning down and populating certain levels around itself. And actually you are in a situation when the Compton wavelengths of the particle is of order the size of black hole. So it's populating hydrogen-like levels around black hole. So the way to think about this whole system is that it's really like huge gravitational atom in the sky. So instead of nuclei, you have a black hole sitting in the center. It rotates. What it does, it populates particles on certain levels. But the important difference from usual atoms is that what you put on the levels are bosons rather than fermions. So you may have many particles sitting in the same state, and actually what typical occupation numbers which you end up having here is like 10 to 70, really huge number of particles sitting in the same state. So it's very rich and interesting system, and it's really work in progress right now to figure out all possible observational consequences of this. And so one clear signature, one clear way to look for this is that, well, if you have a particle with the right mass, you don't expect to see rapidly rotating black holes with a mass with a size which would match the Compton wavelengths of this particle, just because they would spin down by creating this cloud around black hole. And so the main message from this figure, so here what I have shown the horizontal axis is the black hole mass, and this is black hole spin. So the main message from this figure is that there is really already data being taken. So there are crosses here which corresponds to measurements of galactic black holes in our galaxy and nearby galaxies. And so, for instance, and if there were a QCD axion with these parameters, so you would not expect to find rotating black holes in this whole region. So existing data already sets an interesting limit on the parameters of the QCD axion, but in the future, when more data points are out and the error bars shrink, you may really hope in this way to observe, to detect the QCD axion and also these other light axions, because this would be the picture for much light axions. So here now I'm drawing masses of galactic black holes. This is 5 × 10⁶ solar mass, 10 to 7. So for instance, if there were axion with a mass around 10 to -17 electron volt, then you don't expect to see rapidly rotating black holes in this region on the black hole mass and spin plane. So you can really, and as I said, so interestingly, so this mass of axions relevant for black holes, for black hole measurements, it's all anthropic. So in this way you can really see or rule out the presence of axions in this mass range. Of course, so as I said, the whole system is very rich. So you can think about more direct signals from the system. For instance, gravity waves, really from atomic transitions, from transitions between different levels in the system. So they would follow basically hydrogen spectrum, it will be a Bohr spectrum. And for instance, for QCD axion, the relevant frequency range corresponds to advanced LIGO frequency range. Advanced LIGO is a gravity wave detector, which is, well, LIGO is operating now and getting actually interesting results, interesting limits. But advanced LIGO is the next stage of this gravity wave detector, which is about to start taking data in a few years. Also, you can try to see directly the presence of this axion cloud around the black hole by carefully monitoring the metric around black hole. And again, there is a program for doing that. You can do it now for supermassive black holes. No, not for stellar mass black hole, but for supermassive black holes with low frequency gravitational wave detectors. You can really very accurately map the metric around black hole. And there are other thoughts. So basically, it's very preliminary, but there is a hope that so these axions, they also interact with photons, so there could be periodic radio wave signal coming from axion converting into photons in the vicinity of the black hole. So black holes in this scenario could become sources of long wavelengths, almost monochromatic radio waves. But that's the most uncertain part of this whole thing. This is really a work in progress. So to summarize, well, I started with this philosophical argument, but I think it's very interesting that actually now we're at the stage when, well, this argument repeats and repeats many times in the history of science, and actually sometimes one side wins, sometimes another side wins. And I think right now we may be, again, at the moment where this argument is very relevant for actual observations, and upcoming data may tell who is right in the current stage. Thank you very much.
I'll start with the questions, Sergei. Could you go back a couple of slides to where you were showing where current black holes have been found? Yeah. So the black hole spin down is linked to the QCD axion by the QCD axion's energy.
Yeah, by the mass, basically. Yeah. Right. So yeah.
Okay, could it be that it might be another particle that might have the same energy as the axion? Can you say how you might rule that out?
Well, no, that's because a good question, because all what you measure really a mass. Well, there are other ways. First of all, well, what we really mean by axion, so it's not that easy to get a very light particle in physics, because usually, so these are bosons. So usually there are contributions to the mass which usually small mass is not stable. So you need some special reason for the mass to be small. So in a sense, Axion. So I didn't go much into the detail, but there are several. So Axion is really example, and almost the only example, what we call Axion, not QCD Axion, but in general Axion, is almost the only example of a situation when you naturally get small mass. And it's related to the fact that I started with something which is very light, and then to get a contribution to the mass, you need to consider a loop of electrons going around this Aronoff-Bohm line. So in a sense, it's almost semantics. It's almost by definition what we call these axions is naturally light boson. Now the question whether it's QCD axion or not, just some other axion, that's way more subtle, and that's one reason why this radio wave signal would be interesting, because that would be a probe of coupling of this axion to others to something else. But yeah, in principle, from this plot, you just deduce that it's particle with a certain mass. You don't know exactly that this is QCD axion. Yeah.
Okay, and when you're counting the number of axions and getting your anthropic answer, how are you distinguishing those? Is it by mass again? Like you're looking for different.
Yeah, because each black hole, so you see here, so this is particular, this is spin down curves for some particular choice of mass. So the same way here. So here I picked a mass of a certain particle, so that's how you expect black holes to spin down. So if you have lots of data on spins for black holes of various masses, then really you can nail down you see how many particles with different masses you have in your theory.
I'm sure I missed this, but didn't you also say early on that the mass of these axions is somehow fundamentally related to the vacuum energy? That is, the vacuum energy somehow feeds these things, or even produces them? Is that, did I get
Well,
that?
no, the relation was that just the dynamical ingredients which gives rise to these masses, to these axions, they're the same which gives rise to lots of this landscape of vacua. On the other hand, what fixes these masses, well, so this is the mechanism which I just told. So roughly you need a pair of virtual particles going around this handle in your compactification manifold and annihilating later on. And what this tells you that actually that the masses of these particles, they're very sensitive to detail. So if you just perturb a bit your manifold, the masses will change dramatically. They're exponentially sensitive to the sizes, for instance, of these handles. So really, we have no good clue for where to expect these particles to be, because just changing a bit your compactification manifold, you change mass by many orders of magnitude. So that's where QCD axion is important, because as I was trying to explain, so you start with, so we have a good indication, good reasons to believe that QCD axion is there. On the other hand, there is no anthropic reason for QCD axion, so we don't expect it to be as a result of fine-tuning. That's why we expect that there should be also a bunch of other light axions. But this is really expectation. So it would be just very strange in such a situation when, in principle, you could have hundreds of these particles to have just one, and which have no anthropic reason. So that was the bottom-up part of the argument.
I have another question, actually. So, are you expecting the Penrose process of generating these different energy levels to happen around every black hole, or is that something that depends on what's circulating around?
Well, you need the black hole size to be not that far from the Compton wavelengths of the particle which is there. So you see from this plot, so yeah, roughly it's 1-2 orders of magnitude in black hole mass. So each particle affects the mass range of 1-2 orders of magnitude. But rather than that, so you need black hole to be spinning. So for stellar mass black holes, if it's supernova explosion, that usually you expect black holes originally to have a high spin. So if there is an axion with a mass in the right mass range, it would be affecting dynamics. For galactic black holes, again, because if there is accretion, then accretion it increases the mass, but usually it also spins black hole up. So like this black hole grows and its approach this region, then it gets affected by the axion. But as I said, so roughly each black hole, you can think of it as a detector for particles in some mass range, roughly of order 1-2 orders of magnitude. That's where it's sensitive.
Any other questions?
Actually, this concept of multiverse, you in your abstract, I got the impression you were talking about unobservable parts of our universe having different properties.
Well, that's
so. Is that what it is, or there?
Well, it is, yeah, but it's not clear even what to say. What is the meaning to give to this when you're saying that unobservable part of our universe? But yeah, in this picture with Axion, for instance, yeah, the picture is that. So I didn't go into detail. So I said that the amount of dark matter which you get depends on where you locate it. But in natural context, so in cosmology, there is a theory of inflation. So naturally, it comes out that the scale for variation in space for this amount of dark matter is much bigger than the part of the universe which we observe right now. So it really, yeah, so really on scales much bigger than the universe which we observe. In this particular example, amount of dark matter changes, and actually. Because universe is accelerating, it doesn't help for us to wait longer so that we'll see more. Because of the universe acceleration, actually we'll never see those regions. So that's one of the very puzzling things about this whole concept, because it's something which you cannot observe directly, not even in principle, because it's outside the part of the universe which we're observing, and because of geometry of accelerating universe, it's not observable even in principle. So that's one thing why people really worried a lot about this whole concept.
Okay. Well, I for one am really glad that we videotaped this talk so I can watch it again and try to understand it a little bit better. So yeah, as a memento of your talk here, we'd like to give you a little SETI Institute pin, and if you all join me in thanking Sergei.
Thank you.